Okay, I've already started the next one. So start a ratio test. So when I plug in n plus 1 in for the term, notice there's no fractions in this one. So when I plug in n plus 1, this is what I get. And then I divide, remember, by the original. So this time there's no flipping and multiplying because there's no fractions. So I still cancel what I can. And notice I'm left with just x times n plus 1. So what now? Well, n is going to infinity. If I take infinity times x, this is going to go to infinity. Well, infinity is certainly always greater than 1. So the ratio test says that our series is going to diverge for all values of x. But it's actually not quite right, because there's always one value for which the power series will converge, and that's at its center, which is why number 52 asks us what's the center of each of the power series in 51. So let's talk about why that's true. So the center of this power series is 0. How did I know that? Well, the center, if you looked back on your notes, was something like, we're looking for, if it was x minus something to the n, then it's what you're minusing off, that's your center. So here I'm clearly subtracting nothing, or it's x minus 0 to the n. So in this case, my center is 0. And why do I know my series will always converge at the center? Well, let's plug 0 in. If I plug 0 in for x, what happens to my series? Well, I get the series 0. And of course, the series 0 will always converge. In fact, that's by design what will happen. If your center is a, if you plug a in for x, you're going to get 0. And so at the center, you'll always have, so it always always converges at the center because you get the 0 series. So for what values of x does this series converge? Well, it only converges at x equals 0. So you have to be careful with these cases because the ratio test makes you think it's always divergent. And why did we not catch it? Why did I have to know this special exception? Well, it's because I wasn't really careful when I said that this equaled infinity. This only equals infinity. If I take infinity times any real number that's not 0, I get infinity. But what's infinity times 0? Oh, that's one of those indeterminate forms that we don't really know. So in some sense, what we could do is just check it separately, right? If you put 0 in, you get the 0 series, and so you know it always converges. So the point is, ratio test, if you're careful, will actually tell you the values of x for which it converges. It's just you have to think about infinity times 0 separately. So, but you don't really need to worry about that. If you always just know the center, it's always going to converge at the center, then you're fine. All right. So we're now moving on to page 30 in the notes. And so I know you can't read this, but you have it in front of you, so I just want to point to something. So you have what's called the radius of convergence for a power series. What is the radius of convergence? Well, the radius of convergence, so there's 3 cases you should have noticed so far. So the first case was like the 2 problems we did first, which were the first 2 examples we did were something like this, when we found the values for which it converged. So the radius of convergence, in cases where we get an actual interval like this, is going to be the distance between the center and one of the endpoints. The center in both those examples was 0, and if you think about what this interval is, the center really will truly be in the center of these intervals. That's why it's called the center. Excuse me. And so the center in both of these cases is 0. The distance from there to one of the endpoints is 1. So in both these examples, the radius of convergence is 1. In the case where we got all real values for x, so not this problem, but the previous problem, the series converged absolutely for all values of x, we would say that the radius is infinity for that in that case. And then the series, if the series only converges at the center, which is like this problem here, this is this third one, it diverges everywhere else, then we say the radius is 0. So this radius of convergence is really supposed to be just giving you a sort of a feel for, like a visual for on what values will it converge. So next in the notes, I just give you some visuals of what I mean by this. So I give you the natural logarithm function and its power series. You don't have to yet understand how I got this power series. You will eventually. I hope you can see this. Okay, a little bit. Anyway, you see it in your notes. So this power series is supposed to be equal to the natural logarithm within a certain radius. So in this first picture, I graphed the natural log function, and I graphed this polynomial up to, what was it, 6th degree, and we could see what it does. And then the next picture is the natural logarithm, is the bold one, and then I went up to the 11th degree. And so what you're supposed to notice is that in both cases, the function, the polynomial, tries really hard to sort of hold on to the natural logarithm function within a certain interval. And so, as it says here, notice that both these approximations can only hold on to the function until about 2. In fact, using the ratio test, we can show that the interval of convergence on this power series is between 0 and 2. So that's what you're supposed to do on the next page for number 53. So you should actually do that without me on video. So there's your power series. There it is written in general, right here. You should do the ratio test on it and see if you can get that it converges for values between 0 and 2. And when you check the endpoints, it would diverge at 0 and converge at 2. But the point is to have this visual of the function actually converging, the polynomial converging to the function. And we could say the same sort of thing for this next one on page 31. We have the sine function and its power series. Again, you don't need to yet know how I came up with that. And this one's a 5th degree polynomial, and this one is an 11th degree polynomial. And in this case now, the polynomial just keeps hanging on longer and longer. And if you wanted to do this in your calculator and do like a ridiculously high number, like a 51st degree polynomial or something, then you'd see that like you could really make the window pretty wide and it would still stick on to the sine curve. So in fact, this is what would happen if you have an infinite interval of convergence. It means that you can make it converge for as big of a window as you want it to. And so again, 53 is asking you to confirm that. So do the ratio test on this one, and you should get some result that's greater than 1. And the ratio test says if you get something greater than 1 or infinity, then you know it's going to converge for all values of x. So you should take the time now to do number 53 and converge, check those values for convergence. So now I just want to say one other thing that I keep saying this word interval of convergence versus radius of convergence. So interval of convergence is what we've been doing here, where you're checking the endpoints, where radius of convergence is slightly weaker because all I really need to know is what's the distance between the center and the endpoint. So if I ask you for the radius of convergence, then you could just tell me without having to check the endpoints what the radius is. So it's less work if I ask you for the radius, because you could just say what the radius is without having to check the endpoints. I don't feel like I'm being very clear there, but hopefully you understand what I'm saying. All right, so I'm seeing in the notes there are now 2 more examples, 54A and B, that you should do for practice, and then you'll be ready for homework 8. And now I'm seeing that we're ready to move on to term-by-term differentiation and integration, but I am beyond exhausted, unfortunately. And I think I will have to stop for now. It is, in fact, the topic, this next one, that I've skipped before, so I wouldn't be too upset if we had to skip this. And anyway, I will do my best to try to be in touch with you guys via email, but please feel free to ask me questions And I hope that you guys can sort of fill in the blanks well enough without me. And I apologize for class this week. All right.